So you guys know what it looks like there. All right, so let's go. Let me confirm you can hear me. Testing, testing. So you guys know it. Okay, good. Anybody here this morning? Good morning, morning. Okay, let's do the disclaimer and whatever else I got to do. So this is just data. You know, it could be wrong. I could be interpreting the data wrong, and we can always adjust that as we go. But it'll be a nice working point. I'm going to use the OSHA and NTSB to talk about what I'm going to show. I'm going to jump into it instead of giving the background data too much. I'm going to jump into it. This right here, this piece of concrete right here, and let's jump to the NTSB report. This is what the core samples are looking like. This is the general concrete composition. There's a broken piece here. Where did they get that from? That's not even the curb size, is it? What's up with that? All right. Also, we know, I've mentioned in other videos, you can see where this is where they closed in their post-tensioning members. I believe this is just a closure concrete with white paste, that whatever it might be. It appears to be around here, signifying itself around here too. Maybe it exposed itself when the water from the core sampling showed up. You guys want to troll something? You go there and you look at the OSHA, being OSHA. You know, how are they performing this? Just for fun, right? Because we see OSHA working now. Safety glasses, hard hat, gloves, loose open vest, spinning device, guy photographing. I don't know if that's an OSHA person photographing, but clearly this is a rotational spinning product that could throw something towards, off in any direction in 360 degrees. Glasses, no gloves, okay. So we can't really mess with that there, can we? We can try to see if they're using a GFI on their plug for this. That'd be very interesting, right? OSHA person, no pad protection apparently. All right, moving on. That was just fun. This is OSHA, right? I said NTSB a second ago. I mean NTSB second. Oh, whatever. It's NTSB, but apparently it's NTSB. So here's our core sample. That was just a little fun deviation. Look in the background here. There is number 11. That's the 11A, I believe, in the deck. There is no shearing there, as the report shows. That's standing there pretty proudly with a pretty sharp turn on it. What is this? If this is down here, what is this? Let me zoom in. I am zoomed in as far as I can go. You guys can find another image. What is this? It appears to be the top of the post-tension bar, number B, the upper one. I'm calling A the lower and B the upper in this video. If I got it conversely the other way, so what? Take note of these caps. These are outside. They're not damaged. They're sort of in plane. Let's go. Let me grab an image over here in the form over here. And this is what I'm calling B, A, the lower one now. This is A, and this would be B. A and B. What is this? What is this? If this is going into here, what's this? I'm confused. This is the base. It ripped through. What are we looking at here? This one's got me here. What the hell is this? This is supposed to be the bottom of A, number A, post-tension bar in the deck only, which we can verify that. And this is the top upper part. What the heck is this? And then, so this ripped out, as you know. So to start the ripping process, if you go to the video or just look at it logically, this had to stay up while this went down, the deck went down, and it ripped it through. As somebody said, like a zipper. I thought that was an excellent way of describing it. because it's going through stirrups. So excellent. This shows that no ripping took place in the top of this besides the failure, which we know that it's all cracked up to begin with. So that was just that didn't take much to limit itself to right there. And that's the size of that. That's a beautiful shot of the top showing that during the failure, the loads of that hinge went up, and so we can start figuring out what forces were experienced, and we come to the drawings, and this is the hinge right here, and we're looking at the top of it. So this part right here, to some point, became dislodged, which means it took a force there, which is very interesting. Wish we had cracks. Like I said, I wanted images of cracks above here and all up here, but no one's presenting those images as far as before the bridge collapse. After the bridge collapse, they're just trying to put together a story. Profile grade line of this is right about here. This is where they build this design off of here, a working point, if you will, and it's right off dead center of the structure of the pipe, and it appears this is it here and here. Interesting enough, would that create two profile grade lines? Because if that, oh, that's not one. It just looks like it was one there. Nevertheless, this is out by 2 1/8 inch. I think we talked about that in previous. I know we talked about it in previous 2 1/8 inch out. They made this out of plumb by 2 1/8 inch by design. By design, it was out. It's made with the out of plumb level. Here is right here. This is the profile grade line where they work from, and canopy working point. So I'm going to say that's the canopy working point. If I look from right to left, left to right, however you want to do it, they appear to be dead center of the 1'9", the dead being dead center also of the 16 foot. So I'm going to say that the working point and the profile grade lines are in line with each other, plumb, if you will, with no deviation as this shows here. And so that means that these two dots, these two lines opposite of each other, is just killing me here, because I can't figure out where this 2 1/8 inch, where I'm supposed to be looking for it. Is it only up to here? Because this drawing is not very clear about it. Does this appear to only say it's up to here where this 2 1/8 inch creates a hinge at that point? Why the hell would you put a bow in your structure to begin with? That I find very, very weird, the designing of that. I can't think of anything. I could, but I can't think of why you would put a hinge here. This 2 1/8 inch hinge being right here. Why the hell would you do that? So in other words, this would come to this point and this would come out to this point. So this would not be plumb. If you will put a level in the back of this would not be plumb, either from here down or here up. What the hell? I'm confused. I don't even know my front door or the back door right now. So if I put a level here, this would be plumb. And then at this point, the level would be plumb from here to here if I drop a string line from here to here. But yet, it would still be 2 1/8 inch taper on a hypothetical 2 1/8 inch gap coming out, because there's nothing out here right at this point, and it comes back in there. So so if this base is 2 foot wide, you would come out 2 1/8 inch, and then on this side it would be plumb, and then you would come out 2 foot 10 1/8 inch, and then these two would meet, but you really form it up back here. That was just friggin' beyond explanation to me at this point. Not beyond, but just find it very troublesome. That's an 8-inch chamfer here, which a lot of people refer to it as. So you got to speak the culture, whatever the language is. They're calling it a oh heck, I don't know. They're not calling it an O heck. I forget what it is. But look, that's 8 inches there too. It's through about everywhere 8 inches when you see these guys. Look, 8, 8, 8. So when you see them, they're uniform. Don't think they're anything more than that unless they made them more than that. See, they're 8 inches thereabouts everywhere. So when you see them, they're the same. They may look longer and bigger, but it's 8 inches. All right, 8 inches. See, 8 inches, 8 inches, 8 inches. It's 8 inches. Don't get 8 inches, 8 inches. Don't get all whacked out. 8 inches, 8 inches. Let's just close them all up. 8, 8, 8, 8, 8, 8. Okay, so that's now established. You have something to measure from now. You have something to scale from for all you guys trying to figure this out. All right. 1'9". There's your pipe. Now, to help you understand, it's a 6-inch radius. It's an 8-inch pipe. So they do it, that's 12 inches wide is what you're looking at. And then they put the 8-inch pipe inside of it. And then they grout around it or however they decide ultimately to do it. Hello, anybody watching. So that's that. Now, this is going to be very interesting and telling for you. I want you guys to take note of the reinforcement, the numbering. This appears to be this is 12 inches. So we're going to count 14, 15. We can't read anymore. So we'll go with the red, which is 16 inches. 17, 18, 19, about 19 to 20 inches is this reinforcement. That's kind of ish, plainish, right? Level. You know, they should have used a level on this, but we're going to do a workaround, and the workaround is going to look like this. So I'm going to grab and it's going to take some extrapolation, and you guys are going to have to adjust for your own beliefs. All right, so we use a magnifying glass here, verifying some numbers. And remember, red is 16 right here. And we're coming out to the bar he's touching, or she, appear to be a man's hand. 17, 18, 19 to 20 inches. Let's run the magnifying glass around and look at the reinforcement numbers, as you can see. And you look over here, look at this concrete in the background. That's concrete with a nice big stone. Drop over here to the right. Look at this beautiful piece of member here, this concrete. There's just lacking stone. It looks like paste. In fact, this piece of rebar that I would say is rebar is wrapped around there, and it also looks like it just has cream on it, just paste on it. So where's the rest of the concrete mix? Where's the aggregate? Looking above it, where was it? I just saw it. Right, above it to the right. Oh, my magnifier doesn't work that way. All right, so there again, looks like paste. Right here, looks like you can see the stone, the face of the stone. Now watch what I do, and it's just a moment here. Let's come down here. That's that 12-inch hole I told you about. Now it's an 8-inch pipe. I'm trying to find a grout line. I'm trying to find rebar. It looks like a little bit of rebar. We look up top of here, that's rebar. What I call horns, just going to show in one of these. Let me show you some horns, but so he ran his tape measure over to here and put it center line of this reinforcement, not the outside, center line roughly. So we will use center line from here to center line to the underside of this. So see center line, right, center line of the tape. So I use the underside of the tape over here. And let's see, 16, 17, 18. So this is 19 and 20, I believe. At 16, 17, 18, so 19 and 20. So it's between 19 and 20, and it would be the underside measurement that I'm looking for. Let's get rid of this. Now, watch what I do here, and you need to extrapolate because it's an angle. The camera lens does matter based on its distortion and how it's squared or not squared with the subject matter. And apparently it is not squared with the subject matter. We're not looking at it as a parallel. So this will work to some degree, what I'm going to show you. But I'm using a box here, or a rectangle, and as long as I pull on it, it will always keep parallel sides. They're not, parallel. So I'm going to put at the base of this one, it's the one he's measuring from, or it could be measuring from this one here, out here where this finger is, but I'm assuming it's in here, and I could be making an ass of myself, but I'm going to do 2 of them. So let's just use this one first. Put that down the bottom. See the rebar in the concrete? So I can put this at there. Now anywhere along here would be the plane equal with that one. As I come over, I don't find anything matching it, putting that corner there, and I slide all the way over. Nothing is matching this reinforcement. There's no symmetry. There's no symmetry. I mean, even with the angle off, the best thing I can come to is way back there. That's not working for me. I can clearly see that's way above by the pipe, and this is in front of the pipe. So putting this back down there, there's no symmetry about this reinforcement back here. And to cut to the chase a little bit, let me put the box a little smaller. I'm going to show that you can see, let's use this box again. You can see the rotation of the reinforcement before it failed. That reinforcement is going to be 90 degrees. It's going to be 45. It's not going to be this radius here. Looking from this point to this point is parallel. You're not going to, no one runs radius like rebar like that. It will be a 90 degrees. So we will be aligning, fixing this. If that's the 90, we would be bending it not from the top, but probably right about there is the bending moment to put this back into shape. So if I move that over, you see this is the angle that it actually took. It's about 45. I mean, I'm sorry. Let me see that. I'm getting inverted. So 45 would be, let's see, box it. Let me box this if I can. I need to keep it where it is. Now 25-degree rotation before it broke its way free of the concrete of the wherever it's setting in. If this is setting in 12, obviously 11's over here, so this is not reaching 11. It's before the pipes. This is in 12. Here's the thing about that. It's about level with the deck. There's the piping, right? That piping is no more than about 8 inches above the deck, as I showed in other videos. So that's right about there. As I bend this and put this back in place, if I can straighten it back up, it would be right about equal with those pipes. That's pretty damn close to the deck level. And it's also just this, up and a turn. Now, when this fell down, as I stated, it fell down when they released the post-tensioning from number B, which is in line with this one. I put this back here, and you can imagine this being that bar going up. So let's do that for you. So, yeah. So that's that. So that's this bar going up, and let's rotate. And I guess I should do, that's the path. And let's do, that's green. That's not very well, is it? Let's try red. Okay, let's do that. So that's the path of the bar. You have to see it as a plate like this here. They're in line. These plates are equal with each other, across from each other. Here they are here. And they're in line with each other. This, never forget, this plate is standing out here in the blister. Let's go over here to the beautiful engine tips form here and look at this again. Take note that this chipped off, so the forces we need to see more of it, but it looks like it had a torque I'm sorry. So everything, guys, just think of engineering. We say moment, but think of everything you can tell me. You can tell me where your relationships went bad, and I can tell you that's the hinge moment. There's a hinge with everything in life. I mean, tell me something. Your microwave went bad. There's a hinge at some point in that microwave's life. Something went south, and there's the problem. And you can consider it the hinge. You know, your heart, you get a heart attack. At some point, you can trace back to where the hinge effect took place, where your heart was great, and then it went another direction. There's the hinge. It's with everything in life, you can't, a light turning green to red. Right between the two of them is a hinge point, right? The 30-second light, 15 seconds. There's the hinge point. All right, then it turns there. All right, there's a hinge with everything. You need to find a hinge. If you want to find out where things are taking a directional change, it's a hinge. And if you want to change some things, well, you need to create a hinge in your life. All right, as long as you keep living. So hinge really is one of the awesome words. If you can add that to your your wording. If they say, think of one word that helps you out. I have actually 3 or 4 of them. One would be equilibrium. If you want things to be stay the same, they must maintain equilibrium. If you don't maintain equilibrium, a hinge is created and it will go one way to the other until equilibrium is established. And that may mean you're out of that person's life in a relationship, or the microwave will never work again. It's an equilibrium. At the point it's no longer working, it's back in equilibrium. It's a broken in equilibrium product. This is now in equilibrium. It's no longer moving. It's no longer active. It's probably got creep going on, but nothing that's going to kill anybody at this point. As we saw, they walked under it. But during this whole drama, this shows that this stayed connected. It didn't, and I don't know if this reinforcement were straight. This would tell us a story if this rotated, if this bar was straight at one point, like these are straight. This could tell us, oh, okay, at some point to break this off, it twisted at the base to cause this to do that, and somehow it rebound back in. This is the reinforcement as it goes out of the canopy and down into the number 12 upright, that blister, the 10-inch sticking out. This is the reverse of the blister below. So this is their opposite. This is a blister below, and I'll show you a better one. And this is the one above. That rotation of that rebar just shows you is this rebar. See how it comes up and in? That will be similar to this rebar here and into the deck, into the canopy. Well, I believe this might be the one that goes into number 12 base. So this comes up, turns into 12 up here at that pipe height. There's that pipe right here, and here's the plastic sticking up. So you can extrapolate. If you were straighten this out, you would get the height of, we are in the NTSB reports. See the white, the blue upright, this piping here, electrical line maybe. Now, if we were to straighten this up just a little bit, we would see the height of that. So now we can get a little X-ray and as-built now. We're looking at as-builts. Not an as-built survey, but it's an as-built for what we're looking at. You're literally looking at it, and you determine, you extrapolate from there. So let's put that damn pipe back in there. Sorry, I like playing around my voice sometimes. So let's put that back in here like this. Here's the deck. No, I know what's going on. I have to wait a second for it to, get rid of that. So let's put that back in there. Desktop. Images. All right, let's put that back. Let's put that reinforcement in there. Use your own product, obviously, for this. So let's establish the deck. I'm going to leave part of that deck in the line here, so you can see the path without being too corrupt. And then this will be the blister that we're gonna show here. I think I'll change the color for clarity. And I am not taking liberty. There's a pipe below this, so this counts as 0. If I could put it next there, I would. Let's see, I can text. I'm just saying, oh, you guys might like this. I'm calling it 0 force. This part's a 0 force member of this blister. I hope you guys like that. There's a crack somewhere about here and here, a tension crack. So we'll add in a couple of little beautiful little cracks here. and you'll start seeing really. Oh, because I'm in there, it won't let it changes. So I got to take a little bit of. That works for me. I think there are 2 cracks. So there's one there, and there's one about there. So there's your torque act. There's your hinge action if you start to develop. Now let's grab this guy here, and let's do. Yeah, let's do that, and let's do blue. Here are the pipes here. So how can I do pipes? So pipes go all the way through they're part of the securing of the right about there. There's a part of securing the bars down. So I'm going to give it's not there yet, so I don't have to put jack in there yet. There's no bar I have to put in there. So then I grab this. I now grab a bar. Let's use this pink. Hopefully it shows up. And I'm reaching that. It's only going about there, that bar. So we see the deck ripped off at the back. So I'm coming down here like this, and it goes into the deck, into the diaphragm. And yeah, I'll take that. So that is roughly what we're looking at, that bar. And that bar has a slight bend in it outwards. So that's telling you what's going on there. It's just a slight bend right there, right? So can I overlay this? So that's what it looks like if it was green. Let's try that. And let's take a peek at the member again. So right here next to us. So that's it there. It comes up back of it comes up right outside of, see the black part here? See that? So what you look at the plane of this, are we looking beyond that? Or are we looking, are we looking on this side of the pipe or on this side? See the pipe here? We're on the opposite side of the pipe. That puts us, we are looking at that blister. We are looking at the blister reinforcement at this point, is what I'm stating. Because here's the pipe. Here's the black part. The black part's in the deck. The only thing outside the deck is the blister. So this is the blister accomplishment we're looking at. Yeah, whatever. You guys figure out the damn word. Embry's in here. Fix me up, Embry. Fix my wording up, baby. You're good with fixing my wording up. So this is the blister reinforcement we're looking at. Now we look at it as, and please, guys, in the other forums, I know I love attack you. I have no choice. You got no choice. I have no choice but to attack you. I want you to use this data, and especially computer guys and other people, and run with it. Epoxy Bot, I like his stuff. He understands. I think a long time ago he changed towards me, and I don't want to turn him against anybody. But it looks something like this at this point, and it stops short of that pipe. Let's confirm that. Here's the pipe now. It's the second pipe it's stopping short of. Or apparently, remember, I got to scale this crap. That pipe has a break in it, a hinge. What the hell created the break in it? Apparently, the reinforcement kicked over the top of it as it rotated outwards and bent it. And we can now even start extrapolating, aha, look, it's in line with the center of this 4-inch pipe, as they state, is 4-inch pipe in this report. So we're only looking at about a 2-inch inbound on this. We just need to know where it sits in line with the PVC piping. Considering this would be plumb when you install it, not on an angle, then this looks like it'd be an inbound about 2 inches. So it looks like our total shift to the left is about 4 inches. 4 inches at this point compared to this point, considering this was probably over here, is what I'm saying, in line over here. So this makes us get a shift here, hinge point pushing that way. Hinge point would be down here. Hinge point could be up. The torque action could be up higher, actually. The hinge point could be up top, a little further in line, like this. In other words, let me do this. So in other words, I'm correcting my hinge point for you. let's just do this. Let's just grab this, put this in a line here, and you start seeing what's going on here. Center line of the reinforcement. And right about there, because that's straight up and down here, if I do that for you, you can see the hinge point now. Yeah, that didn't work, did it? Very abrupt hinge point, if you will. So there's our hinge points. And this might get identified the amount of the because remember I have to extrapolate. Photography is killing me here, but I'm using things that the camera can't distort, and that's the reinforcement and the theoretical building of structures where the reinforcement wouldn't have been on a weird angle, that it would have been 90. So if I look at these two, maybe now I can figure out, well, that's damn near whatever, to figure out how to straighten these back out. So to straighten these out, I would use it. It would tell me what's going on. So I would do that and that. That's the way it should look. But it's looking like this. So you have to figure out how much deformation it had, how much it deformed by. I'm going to show you another way to attack that. Back to the base again. Whoops. For you guys. So you come here again. We're trying to find a symmetry thereabouts, and I don't see it over here. Am I looking at it right here in this cluster here, and the camera's throwing me off at that much of an angle? It sure can be. This could be my cluster. I would need to ideally, I want to see symmetry, and so I'd want to see the grouping come out the same. 1, 2, 3, 4. 1, 2, 3, 4. But then I would like to see the reinforcement the same. But I'm gonna give you more data. Just bear with it. So what I'm showing here is this looks like some type of weird stirrup thing came out and around going that direction. That we are looking at the blister right now, the part that took the bump on the deck, I believe, that pulled straight up. This is the reinforcement from that. We are looking at an as-built after. We don't have measurements besides this guy's thing. So there's no guessing they do here besides the angles, what's going on here with the measurements. But we are looking at it. We're looking at a bar here, another bar here turned 90 degrees. That's nicely done. I think this is actually part of the drawings. This one here is a real reinforcement design. This might have been the one sticking out. There's some bars sticking out the deck. Some of them took a ride down off the pier and got redirected. So I'm not sure if this was it or not, if this is one of them. He has his tape measure there, but at least nobody measures like this if they want to measure center line. So I established that he's using center line over here. So this wouldn't be center line here, or this engineer or this person took the photograph doesn't know how to use a tape measure correctly. That wouldn't be center line. So I'm thinking center line, looking at all these guys, and we're in the plane. I need a contact point. He's contacting here, and he's contacting here. It could be that he just threw his tape up there and measured across that these are not the same, this one and this one, but I'm going to say they are, that these are two outer reinforcements of the so I'm saying, in other words, I'm saying that he doesn't know how to use a tape measure. And we need to add one more thing to this air problem. Look at this bar here. It's outside the tape measure and it's smaller. Yet at the base, it comes along next to the pipe. So this one did get flexed up, probably riding down on the pier, and that's how you're able to get this weird angle that is not parallel with anything else. So it's not parallel. And use these tricks here when you're doing this. So let's grab this, and I'm going to put it in line with this bar here, and this is going to help me find everything that took a torque in that direction. Let's move this out of the way. So I got one bar there. I slide. Ooh, yeah, that's going to have to delete it and start over now because I deformed it. Look at this. Nothing. This one bar all on its own. This one bar here now, I would throw it in the trash, just about, and maybe the one behind it. These two bars here have their own little action going on. That's, maybe that's reinforcement, but let's go ahead and now let's start finding the bars that all work together. And as I lied, these guys work together. This one works together. That one works together. These don't. So that's a different direction. So we got a direction here, and we have a different direction here. These all group together. So there's our torque action. There's our torque action. Then we got another bar, these bars here, right? So this is the bar here, lining up with this one. Here, 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 here. Oh, this grouping, that one. This one, no. These two, yes, they're in the same plane, if you will. This one and these two. So we put these two together. Now I'm going to show you that. So what happened was that till this grouping here, this shows that the bridge took this end of the number 12 took a downward hump initially when they released the load from number A and B. This didn't do anything. B took a drop down. The forces went down. It created a cracking. It was stopped by the reinforcement. When it was stopped by the reinforcement, we could be looking at what stopped it, that bar and also this slight deformation here. This could be that deformation that we're looking at. It also had a torque action back upwards, a rising action, if you will. So this could be just that. And now it's totally broken itself free, though. Also, maybe maybe it's nothing now. But it did during failure. This stuff held on because this had to be bent. It can't be bent if it's not holding on. This is not really bent in the same path as this. So I'm guessing initially the initial break broke this reinforcement to the left side of the deck as we see it from here. And then during the failure, all the right side of the deck, this part participated in trying to hold hold everything together. Let's show that. So that's my quick summation. Now look at this pipe here, this number 12, this blue and the reinforcement. Let's go to the OSHA report. And let's go to blue and reinforcement, right? That's what I said. Excuse me for sniffling here. I've got a bit of a summer cold. So that's that reinforcement sticking out. I mentioned it took a ride down. Isn't that contrary to what I just stated, though? Isn't this reinforcement? It's pretty far away, isn't it? This looks like it's here. So to get you guys aligned, we're looking at, I believe, the blister. That's a human, I believe. This is his ass, and that's his shirt. And I can't. And there's some plans apparently. But this looks like it's excuse me. It's diagonal in its support. There's the back of the pipe. There's the internal of the pipe of the drain pipe. So we can line it up. It goes right through his chest if we can line it up. That would be the underside of, so let's do that. Let's do this real quickly because I know I can see it and you guys maybe can't, so I don't want to trouble you like that. Let's just do it. Let's just do this real quickly. First off, let me see if I can steal some information, exposing more. Okay, we got little chippers out here. There's the wow, some more here. Reinforcement, they removed that. I changed the contrast and it gives a profile of the cut. See, because lighting, the pixels are here. They have data in it. And so basically I don't have a raw file, but I'm still using a JPEG, a screenshot, in fact. rather. And now I'm using this to grab what it could grab. And here are the pixels. You can see pixels. So this would tell me, using these pixels, his camera is level this way in relationship to where we're looking at, or is that my screenshot pixels? Um, and it would probably be my screenshot pixels. I would have to, it's probably my screenshot pixels. I don't know. I don't know because I am exposing the image. So it looks pretty uniform. Whatever went there, as a tool that looks pretty uniform. The form work, you can see consistent patterns. We got some highlights here. That's a hot spot with the photography. This would be the red. It protects the impalement. Let me just take one more little couple of hits on these real quickly. All right. Just trying to see what data I can find real quick just by doing that. Okay, the clouds are in the background there. His camera. So this tells me about his sensor. Sensor is doing well there. We got some data we can snatch out of this. If we had a raw file, I'd really tear this apart. Okay, one more time. All right, we're good. So auto levels and reset. And let me just add a little exposure to it and a little contrast. Trying to bring up the background, the shadows. So here are the shadows. This is that pipe is sitting on. And let's go ahead and add this damn thing in here now. Let's see, markup. And let me give you the pipe, the path of the pipe. So I got to do some little bit of extrapolation here. And I'm using this as reveal. And then I'll do the same thing again for reveal. This is going to be the drain pipes path. And identifying the blister that I call the blister. I had a better name for it. Now I forgot it. These appear to be about the same distance. Okay, yeah, I'm going to go with that. So you can see below the, if that's it, this is where the blister, if you can, let's do this one. So that was kind of lucky. That was kind of lucky, actually. And one more, because I think you'd like this one more better. Let's do this. So now you can visualize, let's see, something like that effect. B, and let's give you for, right. And somewhere about even with the deck is A. Can't rotate that. Sorry about that. But let's show you that. So here is A, and I call this B. You see how it's even the outside of the deck here, and then this is back here. So you can see where I'm letting you visualize or see what I see when I look at these drawings. I see the bar way back here, and I see the other bar up here. Using this angle and using X-ray vision eyes and putting back some materials, we see that right about here is where everything's sticking out. That's his ass. That's not the pipe. Black pants, apparently, and white shirt, bent neck. Here are the black caps going all the way down, and this reinforcement using sort of this angle here. This or the rest of. Let's change that out to red or whatever. So the rest of that blister comes down to, and not touching the ground, it comes down to the end of this member here. But it's just crap. It's just nothing, right? Because it's below that pipe. That point is structurally, well, I like to troll back now, a zero force member, zero force participating concrete, unless it was shimmed. And then I put it back into action, but kind of weirdly, I put it back into action, but in a limited capacity. I mean, hugely limited, because it has a 12-inch hole through the center of it. It's 1'9" in width, 1'9" in width. So I have to take the hole, put a damn 8-inch or 12-inch hole in it, and then an 8-inch pipe. So you do the math: 1'9", 12-inch hole, at least 5 inches, at least about 2.5 inches on each side of a load path that it can go down on each side. So for visualizing you guys on that, right here, here's the hole, the pipe. This is not showing the blister, but the load path of this 1'9" has to go through this 6-inch radius, which is really a 12-inch hole. So 1'9", 12-inch hole. If you can line these up, you see that's only, what did I say, 2.5 inches on each side. So that's below there. That's a 12-inch. This is a 4-foot deck, right about here. 4-foot deck from here to here. 4-foot diaphragm. So everything below that is just throw it in the shit can, throw it in the trash, pretty much. It is a radius, though. You could do some really argument with me about arches and how they transfer loads and all that. You might be able to own me on that one, because I like arches. So there's those pipes there. Let's go to, lost the image. So, oh, that's the image. That's the one we're looking at, the original. So there it is now. You now see the load path. You see this reinforcement that's sticking, going out and coming up, is not beyond where this is. Now, maybe they straightened it up over here. I don't know. But let's look. We're in the FIU. We're in the OSHA report. But this reinforcement standing proud, straight up. As we look at the OSHA report, though, this appears to be touching the pier. But yet we have this sticking out further than this all day long, right? It's beyond the caps. Let's look at that real quickly. So what I'm looking for is the deck image where they're standing on the deck and they take photographs. See where I'm going with it. And with the banner in the background. Yeah, this shit's in my brain. Memorized. Right here. Here's the banner. I think there's another one. Yeah, this one. So here are the red caps with the concrete sitting on top of it. Awesomely so. This will tell you that all this debris, if you were going to put it back together, belongs in the everything above it, either 12 or 11, or the blister. I had a better name for it. It's part of the deck, incidentally. But this tells you it belongs there. Look at the grading of the concrete, if you will. Grading meaning the gradation of the stone. As I stated earlier, the gradation, this is not, this is a screenshot I took. This is lacking that gradation. Now, OSHA and the NTSB said the concrete passed all tests. You know I'm biased against NTSB. I guess they won't hire me for shit, but they hire me to troll them. But this is lacking. This is just cement of some type. It's theoretically I'd call it concrete still, but with a smaller gradation of stones. So here's our this is awesome. I said it one of the videos. If you can match the black plates up with these skid marks, and these skid marks don't really match up. I mean, they might match up, but they don't really look like, it doesn't make sense. It doesn't come out. But there's that bar right here that he puts a tape measure behind. Do you see where it's sticking out and it's touching the wall? So that's the one I said we can discount because the wall deformed it. It's sticking out. It ran down the wall. These guys, a few of them, we're going to have I wish I had a back shot. We'll have to discount it because they were deformed also by riding down the wall. If we can line them up where they stopped, right here, this apparently, not apparently, 100% this scratch and this are not the same. It's not the path. This path continues on, and this is over here to the left. It would be under tension still against this wall, and it wouldn't have moved over and been able to move this stuff over. So we got to line up all these damn lines along with the deck to figure things out. But this one here, look at this guy here. This one is the one with his tape measure. Right here, this one. This one is the one that ran down the wall. We can shit can this one, throw this one in the trash because it was deformed by the path of the wall. But we can look at the reinforcement now and see, is it really the way we stated? So here's another photograph, kind of same angle of this direction of it with the photography, just a little bit more, not square, but damn if it's about the same, which in this case will work for us. These two bars here, see the two bars where they come across, and I said they right here where they come even, these two bars here, when they barely make it to this pipe. Now you can start triangulating it, getting it lined up. And here it is with the 3 pieces of PVC coming through the deck. That would be here. 3 pieces of PVC blue piping, flexible piping, or probably electrical conduit, low voltage, coming through the deck here and lining up right there. So now you're starting to get the putting things together scale-wise and measurement-wise. This is, as I stated, just about even. If we were to straighten that up, that makes it just about even with the deck. This reinforcement, which would make a path of, an easy load path for cracks. Just giving you some scale. And I also wanted to show you how to line this up there. So these are the little, I call these horns sticking up. These guys here, and the one here. Very, very interesting indeed. But we can't trust how they became sheared or broken because, well, can't trust the data that we're giving us. We're going to have to extrapolate and work on it on our own. We got a piece here also. So these could be the stirrups. They cannot be the stirrups. They're sistering. They're going exactly around this bar, the number A, I call it. See it up here? That perfectly matching it, but not this one. This one's off to the side of it. So what's the intent of this? I don't know. That's maybe it's a zonal thing they made up for the reinforcement, and it tapers off. Another one should be over here then, but I find it's non-symmetrical. If we look at these two pieces again, do you see them over here? No. And so we talk about torque action and rotation and why one end is imbalanced. Well, you just did it. You created all this reinforcement with conflicting design. It's not symmetrical, and yet you made a symmetrical structure. And well, besides the truss members, the uprights. Now here again is another verification of my concrete discussion about the composition of the concrete. The composition of the concrete. Also a pet peeve about this pipe being removed in the last image, that you can't remove this stuff. It's removed now. You can't remove it. You got to put it back. I don't care if you damn put epoxy around everything or something, but you should have moved it where everything would have been surveyed. You need somebody like a damn archaeologist to do archaeologists. Archaeologists, that's the ones. Do the dinosaur bones right. They go through stuff properly. So this will help you if you use one of these boxes to give you your symmetry. You're looking for symmetrical stuff, but you clearly see symmetry is not there. You can now determine the amount. This doesn't appear to have ridden down the wall. So this is great. These two do not appear to have ridden down the wall. So they'll tell you that Well, they only had a slight deflection. That could have been that initial bump when they detension broke this free. It didn't have the ability. So you see that it looks like, so watch this. So you have two ways to go about this when you think about it. You would say, oh, when it went down, it caused that deflection. Or when it was failing, it caused that deflection. Well, I kind of like the idea of it. It might have torqued this when it went down, given this its deflection over here. And then when the total failure happened, it did do a rotational torque, which gave us this angle here. And that's the total failure. Then it's totally separated itself, broke its way free. Doing so, it also released our magical J bars. Hopefully they have it over here. I just love this image. I really, love that image. I'm coming over here because it makes it easy for me to grab. I can't, every time I go to search, it's hard to hell to search. I have no idea where it is, but here's what I talk about hinging. My man here, Poxy, I think did this. He actually, yeah, Poxy, right? He actually did the, a nice drawing from this where I talk about the hinging happening. This is where I believe that number, so here's the pipe. That number, the 10, sits in here. The post tension, the bars in here. That's the drop down and up. Now, Poxy is the only one, and probably Peyton on it, who's now standing proud and stating that it's hinging also with the upward force. And this will be an attack on everybody in that group that doesn't believe this, so that's why they're letting him ride. They're not talking to him. Thank you, Poxy. Obviously, you're watching my videos, so thank you. This is not false data. Stand strong, man. Stand strong, or girl. This is where we see the material. Where I show that this left side. This is the left side. This is that one right here. We're going to look at. Let's just use the image here. It's just easy to grab them anywhere. But this is where there's this is further in than out right here. This is why I think it took that torque back towards us. And that gap there you're seeing, that's probably this deflection here because it's still in the blister. So this slight deflections probably took place in the release number, when they released it, detention, and it cracked like hell. This is probably a crack like hell. And these took a very, very minimum bend, but there's that torque action, which now is explained and visualized with their tape measure. Going back to the report. Going back to the report, we see it's up and down. Okay, further up, perhaps. We see it's up and down, and there's that bar there. We see it's up and down, up and down, up and down. I'm looking for up and down tape measure, left and right, back of the deck. And where I had a little pet peeve about the engineer. I believe the engineer took the photographs, does not use a tape measure, can't stand up his tape measure vertically, and can't put it symmetrically upon the bridge to take a measurement. I find that, basic skills that shows me that the guy's an asshole. So there's that bar, that this is the first one doing the detensioning. See that much, that gap, that huge ass gap? I believe that's that move when it detention, it dropped downward. So this shows that force now. This is the hinge point. Probably more like, oh, great. I didn't mean to do that. More like right here. That's the hinge point, the drop down, and that pushing away of 12 away from the deck looks like this. And that's that rebar inside this side. And that's that bend you see. When they retensioned it, that bar is not going to now, this concrete's not going to be able to straighten that bar out. And that's your total break. That's my hands clapping across each other, That's the total break of that bar. That bar is no longer participating in this program. That bar has seen its life cycle. It is done. When they retension, this bar, that force is applied back here, and this plate right here, way down here, this number B, finished off the connection, the love affair between this reinforcement and the number 12 pretty much. At the same time, it might have mostly finished off the rubble inside here. that's created from this break, pretty much. And now what's holding the canopy on is this reinforcement here, extrapolating. Okay, so I still want to show you the tape measure. I want to help you guys understand this. This is 8 inches. 8 inches, right? We know that now. Use this. This is 1 inch deep into the deck. This line here is 7 inches approximately. So that's really 6 inches off the deck on this side. Or on this side of the flexing deck, it's 6 inches. And on this side, it's, well, 6.5 about. Then you can come up here. You come across, that's 10 inches. Roughly to the parallel to the top of that pipe sticking out. You go from 10 inch, that's really 9 because you take away an inch or so. You come up here, that's 3 inches, 10 from, I mean, that's 4 inches, 10 to 4. And right there, going up. All right. Let me get you that damn image I said. Let me get you the image. I'm going to call for any apologies. I got apologies from that Roman movie, right? Apologies. I normally say apologies. I thought that was so funny. That Roman movie, whatever one it was called, Gladiator, one of them. So here's those 3 pieces on this side, 1 and 2 and 3. This gets you aligned with the 3, 1, 2, and 3. 1, 2, and 3 is, oops, sorry for the shimmy jam there. 1, 2, 3. Well, they took liberty in this because I don't think they broke like that. Do you? You think they popped like that? Bear with me. Bear with me. I love you guys. Don't go anywhere. I'm showing my love now. I could be working in my yard Saturday. I could be doing so much, but I want to share you guys some love here. I got a lot of stuff I got to get done, but 1, 2, and where's 3? There's a piece there. Tension took place inside there. It was still holding on to pull that apart. 1 and 2, very telling of what's going on that side of the deck. Right there is where it broke, way up here. And the other part of it is sitting on the deck. So you got this pipe, right? It's this PVC pipe here. It took tension. And here's the rest of it here. This would tell you, you know, what, if we can figure out how much of this is left even, it'll tell you where it was still holding or not. And then it broke through. But we get stuff like this that you've got to troll through the data and realize you're being handed a bunch of crap when you see this. This is not one-to-one data. This is not chain of custody correct. This is not correct chain of custody. This is some nefarious shit that we're being handed, or some very negligent form of chain of custody. You can't get data from this. I can't use this photograph on its own. It did not exist like this. You know, it had other debris. It existed like we see it. Here is where you do the investigation. Right here. You don't take this anywhere else. It stays right here. That's like going to a crime scene, right? And everybody says, okay, bring all that shit back to the shop. We're going to look at it. Yeah, and everybody comes back and says, okay, I think that was just throw it down. Yeah. Now let's put it back together. This is just ridiculous. It's just triggered me beyond belief. Sorry, guys. Bad training on my part. I got controlled by myself. But you see my point, right? Is that, don't, as I like to say, don't hand me whatever, don't hand me, I could put in anything. Don't hand me this and tell me it's a pack of smokes or whatever, don't hand me a pencil and tell me it's a pack of smokes. I'm not that dumb. This is still in play at this point, but we know it's getting some elongation. Something's moving across the plane of this. There's the string for chase on it, perhaps. This is the report. I wanted to show you the damn tape measure. We're getting there. Oop. Okay. We're getting there. Tape measure. This is showing why you get that torque now because of the reinforcement, the releasing of the loads. Oh, your reinforcement's gone south. You have an imbalance in reinforcement. I mean, a basic rule that you don't violate. It's just stupid. I don't get that at all. Really, guys, this is at 8 inches. This bar here. If you can find, and that crack is down there. If you can find this in place, you're really going to be able to see the path of this and disregard that crack up top. It's a flexural crack. When we look at the back of the pier. But look, this is right at 8 inches, this bar here. And if we can find it on the pier, it'd be great. All right, so there's, I don't know what the hell this is, a pack of shims. I showed you another one that they took it out of this one, but in this one right here, what the hell is this? What the hell is that? Pack of shims that they started shimming, and that was on 313. And there's another piece of it right here. What the hell are they doing? They trying to put shims under there. The failure is right above here, right above, sitting on the deck, on the pier, is right above this crack line. And that always, what the hell is this, tar or what? They just threw something on there. It looked like burn marks at one point. So there's our separation. To get the separation, we're going to have that rebar bending, or we're going to have the concrete bending going around it. You can't ignore this stuff. There's all the rebar you're going to discount that slid down the wall and turned back up. Apparently the same size, roughly, but you're going to have to 1, 2, 3, 4, 5, 6, 7, 8. 8 rotation, 9, and you got to keep finding it, and then you got to stand it back up. 10, 11, you can go on and on for this crap. Some of it sticks out. This already had an angle sticking there and an angle sticking there. So some of this, when it slid down the wall, some of it could have deformed the rebar that we get a reading that's all standing up right here. So that's the 1, 2, 3, and 4 or 5 inches. This is 7 apparently, so that's 6. There's 5. So it's between 4 and 5 inches to the left. This appears to be a C, but I'm just reaching. That reinforcement I stated on this side of the deck that's way off, and it comes out to right about there, coming across the deck, and very close to inbound of this, very close, which will make a void, a weak point. But this is what I'm talking about here too. Take note of this being further in than here. This might indicate already that this is some type of damn void was creating this pulling inwards. I don't see the rest of the deck going. So I got 2 choices here. All of this material went around this one, and this one stayed in place. Or this one, it's no longer in plane. This one went recessed. This is D1. D1 is only 6 members, and this is 11 or something like that. It's the same amount of clamp force, but this will fail sooner because it's got least amount of cables. But yet it's inbound. So this appears to be that the forces in D1 are pulling inwards and actually creating some type of room was created for it inside there. Some compressive ability took place to allow this to go inbound. D1 went inbound. See the plane there? The rest of these are in plane in the diaphragm. So when this first initial break of dropping of I call it dropping of 12, took place, it took D1 with it, or D1 came along, and there we go on this side of the structure. D1 is totally encompassed in this failure. The transverse cable, longitudinal cable, correction, is totally part of this failure at this point. It's not just 12 and 11 participating in this failure. It's D1 having a little participation, and it's taking a torque action. This would indicate that, and guys, I don't know if I really shared this with you. I still like to see a butterfly effect in this failure with another image, a video showing that 10 actually did kind of punch in and fold over the deck from in to out, And this would sort of justify that, showing that these forces were not, the transverse cables were not loading D1 through D6 on each side equally, because this is a weird ass depression. This is a depression, and you can follow it down to there. But now we look at this again, and there's this is the falling downwards. I state, not the sliding shear as they whatever. All right, so 5 and 6. This if this is 5 inches, right? I've now been able to screenshot, come up with a number off of here that I can stick with, and that is, I'm looking to the right. 4 and 4 and 4 3 4 feet 4 and 3/8 inches. This states is 4'1". So the gap, this is 4'1". So the gap is 3 and 3/8 inches. The gap between the bottom of this diaphragm and the top of the pier. Looking to the left here, my mouse. 3 and 3/8 inches. We're now at almost 5 inches. So we have an elevation change upwards. Even though you see a crack here, don't get this took an action where it went down, and then the canopy's failing, pulled it spring action, pulled it back over and up. And that gives you your higher elevation here. If I were to be able to see under here, underneath of this, I would still see 4, and if you could still see the rest of the diaphragm, you would still see 4 and 1/8 inch out here beyond this crack line. But here you're seeing more because it sheared down with the loads when they released it, went down. And then the spring action of the transverse cable, longitudinal cables in the canopy, C2 and C4, along with the deck creeping downwards, sagging downwards, pulled 12 back in. 12 and also the transverse B only in the number 11 is holding this deck together from falling to the ground. That when they loosened it, it regrabbed, and that started giving a little bit of clamp force left. But remember, that's mostly to the right now with the reinforcement to the right. I believe the reinforcement to the left is about shit. It's about this to the left is about worth about a pack of smokes. So everything to the right is what's holding this on, because we don't see it straightening back up, elongating, or anything else. I think it had its moment. It had its moment in life, is what I meant by moment in that case, not moment engineering wise. So now we have it down. If we take the working point and we were to redo that working point and look at it again, we would see this working point is hinged just up a little bit. It's no longer in plane with the deck. It's hinged up a little bit. Now to the left here, we're looking at about 5 inches, right? And to the right, we're now going to see that. So that's about 5 inches. And to the right, we're going to see this, the right section. This is where I said that reinforcement comes here through this blister up here and turns and comes here. All right, so visualize that. It comes up and turns. But since this bridge took this 12 dropped down and upwards again, that reinforcement took a wrinkle and back up. How about that for a word, wrinkle? This is very telling. This is still plumb, 100% plumb. So we know the path at this point is not interfering with, apparently 100% plumb, not interfering with this bar down. There's no interference here. The PVC pipe appears to be plumb also. So that's good news. It doesn't seem to be taking a crack on that side. That's just data. All right. So there's that crack out to there, and I'm saying it's all encompassing of D1. And come to the tape measure on the right-hand side, and now we see that we're down to 3 1/8 of an inch, 3 1/8 maybe. So the torque at you now look at the back of this deck. Wrong one. You got 3 1/8 over here. You got almost 5 here. So you can see that it's lower to the right and higher here. So it's almost equal where it's supposed to be, but it's a false reading because it's up. It's down and up with a drop, and we see it back here. And the deck is also moving. Don't. It's got creep in the deck. So we're getting a hinge effect. And that's also, those measurements could be, off by 4 3/8, that one there. But nevertheless, the tape measure is not lying, but it is lying to some point because the engineering skills of this inspector, this BPA, on 312 BPA, when I say excuse me, I had something in my throat. You know what I was going to say. He ran a tape measure on an angle, which you don't do because you'll get a false increase in measurement. You see it here. He ran it to D2, outside of D2 down to here. That's 312. We're on 312 the same day. He ran it almost center line of D1 and not quite plumb, but close. And so this would give you a straight plumb real reading. This gives you a false increase in measurement, and false because it's on an angle, it makes things longer. You have a measure on an angle, you're going to get an increase in measurement. Is what I mean by that. Not the increase of whatever, because it's on an angle. It's a diagonal. You're going to get more measurements. If you'd have put it over here, we would have got a true 1-to-1 reading compared D1 to D1. But this guy sucks. Yeah, this person took this photograph. I wouldn't hire him to wash my car. With a PE engineering degree, I wouldn't hire him to wash my car. He has no evaluation skills, zero evaluation skills. With this right here, this is such an amateur move. This is my pet peeve. People who measure on diagonals. I'm like, what did I ask for? A diagonal measurement? What the F are you giving me a diagonal measurement for then? I didn't say give me a diagonal measurement. I said, what's the length? What's the width of the room? I didn't say what's the width of the room on a diagonal. That's a diagonal. Yeah, that's a pet peeve for me. Don't measure on a damn diagonal. All right. He's an engineer. He should know better. But apparently they don't teach that in his school he went to, or any school actually, I guess, anymore. So there's your depth. You lost a plane. A level on this would have told so much. Just a plumb level would have told so much more. All these people lack. I'm triggered now. I'm ready to start cursing. They got me that far triggered. So that means they owning me. I'm so feeling attacked now by their lack of skills, and they're supposed to be skilled that psychologically I want to curse at them. I want to run them off the job. I want to bully them away out of their field. I'm sorry. I'm feeling that much. I'm just telling you psychologically what's going in my little pea brain. So this was a plate they used for a template to do some anchorage of some type. Ooh, I want to show you this. Oh, I got to go here. I want to show you what here or somewhere else. It's in the. So I love this electrical guy. He keeps posting stuff there that's awesome. He keeps and he gets better zoomed in shots. Not that one. Maybe it's not here. Maybe I found it on my iPad. Damn it. I'm going to tell you what it is. Remember I kept saying, want to know how it was supported on the in the impact and the side of the structure? Gosh, it's on my iPad. I'm going to tell you guys how I found it. Maybe you can find it. And even in this group, stop being so damn jealous and just find the damn data and work with it. Grow up. Be supportive of the data we're all trying to get out here. I'm supportive of all the data here. That's good data. Shoot. I finally can get some good. It's undershot. Oh, the guy's on a man lift, and it's undershot. It's not here. He's on a man lift and looking under. When you look under here, though, you'll see a brown pattern, a repeating pattern. That appears to be the formwork that he used to support it on the side of the structure on the over there. So it shows that they didn't load point it. Had the bracing, the temporary supporting equal to what they had here, using what I just stated. I'll try to see if I can find it again. Hey, Bruce, my cat. So looking back at this is where the break is. That crack is. Let's just use this. That crack is approximately right here. That crack. The rest of it is below that crack. I'm going to show you is the bar is number B, and then that's the pipe, and that's just chunk below it. That's why. So right about here, this was right about here. If you could put this back together, this would be right about here. This should all be just junk below it, zero force member blister bar. This is the blister. 10 inches of this back of this is the blister. So don't count that. So yeah. This part back here, this 10-inch overhang, I extrapolated. 2 foot 10.5 inches total. 1 foot 9 is the other way. So how the hell did I get 10 inches? I don't recall. So there's an 8-inch chamfer. That's 3 foot 10.5. So that's 3 foot 2.5 inches from here to here. This is 2 foot wide that they claim in the diaphragm. So let's do that again. So 3 foot minus 8 inches at 3 foot 2.5. 3 2.5 minus 2 feet. My brain's frozen. 1 feet 2.5 inches. How'd I come up with 10 inches? So what I did, you just heard me do my math out loud. So I took 8 inches off of here, right? So that leaves, I'm just verifying with you guys out loud, 3 foot 2.5 inches. They claim that the diaphragm is 2 feet wide, not counting this blister. I had a better name for it. Not counting this blister. So 2 foot minus, doing that loud again, 3 foot 2.5 is 1 foot 2.5 inches. Damn. Really? Really? So I would come in 1 foot 2.5 inches, approximately there, and put in that 1 foot 2.5 inches. I would put this 8-inch plate on a diagonal in there, and then there's that shape of when it dropped down, and all that crap in there. Those bars I said broke free. So I stated earlier, those bars broke free. The right here, I believe, is the path of that bar right here, where I stated that bar here, that these bars, I believe, are in here. This is that bar path. I'd love to be able to see a better shot of this. You guys can beat me to it. Please do. I'll be like, you found it. I'll do a video. You find the damn image. Here is also where bars are standing proud inside there. They took a moment. They caused spalling of all this product to pop off, whether it be a downward or a tension. I don't know, but that looks interesting. That cross piece there is a stirrup, perhaps. And so this is why I'm saying we can see this so cleanly, is that the failure already happened when they're dropped. But I want to find this one image. You guys are going to love this one image that gives that other data about how it was supported in the impound. So this apparently does not exist. All right, where the hell is it? Let me look at my iPad. Let me scroll down to the bottom here. Give PoxyBot. Since PoxyBot is mirroring my data, PoxyBot now gets, obviously my support. Under here, let's see. I'm looking at my iPad. Give me a second here. Bear with me. I got to go back in image, or let me just, these screens, the way it works. I hate to lose the one I have, but I'll go back one. And this guy on a man lift, underside left, camera left, if you will. And he's looking up. When you look up, if you look under the diaphragm, you'll see that. All right, I don't see him here. So I don't see him there. Let me try this. So FIU bridge images. So I did this, and then I said, it's not, iPad does it differently. It said images and something else on the iPad. Maybe I'll get lucky. And no, they're not synced, so it won't work. Chrome to Chrome won't work. I don't have them synced up. So I'm looking for the man on the camera left, or as we look at it this way, looking upwards on a man lift, a single man, and that's going to show how it was temporarily supported. Unless somebody went over, unless they're all like, rain drops, or a stain from water running down, which I try to debunk myself and come up with ultimate answers to a question I asked myself, and that would be one. They're all stains from of all things. Somebody set a repeating pattern of metal up there, and when it rained, it stained and went across it, and they did that repeating pattern because they measured it out and used it to I come up with an alternate way that it can happen. So I leave it open to more data. So I state I state, there it is. I state one thing, but then I say, well, can I account for it differently? And right here, 1, 2, that's a repeating pattern. I think, and it goes down here. I think this is how the form work was underneath. Stain, stain, and I'm saying stain, right? I'm taking liberty. Stain, 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 stain. So this is how it was supported in the impound. Remember, it also was supported by the post-tension members down here in number A and B. And I believe it was already creeping anyway. The deck was already failing because of post-tension errors. Now, look at this profile. This is crowned. Look at this crazy ass profile. And then you put transverse cables across it, all equal. I don't get this profile. Obviously, the computer program and their genius abilities say this profile is the right one. This arch profile in the diaphragm. You look at this. Up, down, over, and the transverse cables come across, all of them. Well, they would all experience a moment differently. The concrete from here to here, theoretically, would be in tension, would allow it to be more, this would fail first, become in tension more so than the one is closer to the transverse cables because it has less of a distance to go. Unless you calculate the moment, you really test loaded this and you said, you calculate the moment with these transverse cables and these loads and said, look, you know what? It doesn't go into tension until 8 inches. So we'll put our cables within 8 inches of this and we'll always keep it in compression that way. We won't create a tension moment in the deck at all by the loading. There won't be a tension loading going on. But if that's the case, why the hell the profile is so amazingly effed up? Why is this so, I'm saying effed up and not in hindsight, just in general, I find the transfer of the loads just friggin' crazy. Why? Is this VSL or is this Erica? I would not say it's Denny Pate. Tell you guys the truth. And I hate saying it that way because I learned in psychology a long time. Somebody says to tell you the truth might mean they're lying. There's a camera, so I hate to use that term. But what I'm really saying is that to go for Denny Pate and going against Denny Pate is what I was trying to state. Is that Denny Pate had, look, man, he did a patent on how to allow post-tension cables to go across individually to act in an individual action across the top of piers. So does this sound like the same guy? I mean, yeah, our brains do change, right? And maybe it changed from then to now. So I wouldn't know his state of mind and his engineering abilities anymore. But let's use that history there. Would that be the same person that would not be able to see that if you change the profile here that it would react differently? It just doesn't hold. Of course, everybody knows changing profiles change the load path. So who wouldn't know that? I don't know who wouldn't know that, but clearly, if that's an assumption, then you say, okay, then this must have a reason. And then what's the reason? Why would you have this higher, these two lower, this less? What the hell? And so my thinking is, I hate to say it and save Denny Pate, if you guys will, but it is a big firm. Maybe Denny Pate did turn this over to Erica and other skilled, other professional engineers to do this. And he just said, I'll stamp it. You know, I don't know about you guys when you were first getting your PEs or not. Didn't you have other people stamp your work? You know, did they go crazy over looking over top of your work or did they not? So, you know, yeah, maybe, you know, in Denny Pate, you're still ultimately responsible as the stamper. But, you know, I don't see Denny Pate being the one that said that did this, that had his thumb on this one. Sorry. Based on, you know, the rest of his post-tensioning love. I see this as VSL or Erica, since her name showed up as party to this. And then here we go here. And her lacking, not her and him at VSL, not making clear in the plan. So I see see, when something's critical in a plan, you make notes, C note. And you would say, and I didn't see one friggin' C note in this whole damn thing. You know, C note, a repeating C note, C note. SEENOTE. I have not found that in one part of these friggin' plans where it said C note, meaning this must be maintained. The grouting must be done before the detentioning. C note. C note. Make sure grouting is matured. C note. Test the grouting. C note. How critical this was. So I'm stating that none of these, I'm triggered because I'm going to curse. None of these professional engineers, how about that, understood the structure and the load pass. C note. Anyway, so here's the blister. Here is the loads transferring there. It may be that since in this group and in many engineers who wrote me all informed me that this is a zero force member. Well, it is a zero force member with no load on it. Take it off and see what happens. See what happens. So yeah, I know it's not a truss system. So if it's not a truss system, you can't think of it as a zero force member. You have to think of it as what is it doing? What is its job? Not the load points and the transfer of tension and compression through these. It's not doing that. The loads are transferring through the transverse cables to the longitudinal cables. So all of you, yeah, I'm sorry for you're not being able to understand that you just can't remove it. You gotta stop thinking that it's a truss system. Okay, so this again shows the profile. See how it's all over the place, and then down and up and then small. This is where the cracks took place, mostly through here. This had a recessed moment in it. Here is the bar here. Here's two rods sticking out next to the 8-inch pipe, lefty and righty. All guys can appreciate that, lefty and righty. This is lefty right there. Righty, I don't know where righty is. That's lefty. Lefty is this one. So see lefty coming up and doing that, coming across. Lefty is telling us how far he bent to. Lefty, if we can figure out where lefty is telling where it bent on the structure, out bending here, and then had a hinge moment here. Obviously, the bridge, it didn't ride the bridge down here because this stuff's in the way. So this point of contact created a hinge moment here. That's lefty. Here's righty. And there appears to be a couple more that you can account, that you're going to have to count for. But these guys, you start accounting for them, you start you start telling a story. So now we see that how they loaded, how they had it in over there in the staging area, how they had to support it. That, and they also had it, number one, had to support it in B. That was helping these forces. But this load, this is not a zero force member. This was putting load down here as proof when they removed the B, the cracking happening this direction. Nobody's going to touch my $1,000. I'll put the bet out there again. If anybody can show me 11 can slide over first through this load, this truss system, as you guys call it, because that's why you have it sliding in this. Oh, I'm in the engineering group. So that's why they have it sliding over here. It's because magically they disconnect this from the rest of the structure. That 11 can slide on its own without breaking apart 10 and 11, 10 and 9, or doing anything else. They use magic, and that's the lack of engineering that they could work for Denny Pate and Linda Figg and VSL, that they can do that all on their own. They can come work for them because they would come to the same conclusion as the OSHA report, that it slid off. Now I just attacked the OSHA guy not by wanting to. So that's what's left. What's left is showing you how things acted. That, what are we seeing here? Well, apparently this is just stacked concrete. There's no rebar. It pulled away. What are we looking at here? Look at this long rebar here. This bar going up here. And this track here appears, and the concrete behind it. This appears to be these upright members here going directly up. Whoops. OSHA report. Going to the bottom. Just telling you what I'm doing with your eyes because the screen's going to go fast. These uprights here. These are the uprights. Now, the reinforcement, it looks like it took 2 bumps. This is standing in the uprights. Remember, some of this that's odd. That one's really got me. How is that sticking out? To me, that means they re-bent this to come back out. Because how do you get that one bending up at the back of here? You get these bending up, but this sticking out. So to me, again, the chain of custody of this material and this literal impound at this point, the real impound, I find the chain of custody to be corrupted, the evidence to be corrupted. I'm still working with it, but I find it to be, that's evidence that it's corrupted. So I can't trust a lot of what I'm evaluating because of the corruption. These uprights here, these guys were in, these guys standing proud like this, standing straight up. Let's go to their shot here. That's these guys here. Very interesting that they're up. They're not bent. They're straight up. This thing got pushed back over. It's a weird failure of not weird. It's definitely explainable. But these are, where's another one? They're pretty straight. So it took a long, it took 1, 2, maybe 2 feet of vertical drop before the rotation took place. So you're looking at a straight and then a rotation. But if it was